Okay, well, thank you very much, and thank you very much to the organizers for inviting me. So what I want to talk about is not really about quantum thermodynamics, but about some general problem that one encounters when one uses superconductors to make basically any sort of devices. So this is work done in collaboration with a former postdoc, Anton Bespalov, who's now in Nizhny Novgorod, with my colleague Manuel Hussein in Grenoble, and Yuli Nazarov, who's a frequent visitor to Grenoble as well. So the most naive idea is if you have a conventional superconductor like aluminium, it's spin singlet pairing S-wave, and you would have a fully gapped density of states. So there are no quasi-particle excitations below the gap energy delta, which is also the order parameter. Which means that if you go to low enough temperatures, meaning temperatures that are much smaller than delta, you would expect that the density of quasi-particles in the system is exponentially small because you need the excitation energy, which is the gap energy. This is not what is observed experimentally. It works well at sufficiently high temperature, but basically in all experiments using superconductors, below a certain temperature, what they see is that the residual quasi-particle density is much larger than what you would expect from this equilibrium estimate, which is exponentially small. So I'm just showing two examples here. The one is for superconducting resonators, where they can measure the quasi-particle lifetime. And while at high temperatures, it follows this exponential law, at low temperatures, you find the saturation. The other example is from the coherence time in superconducting qubits, which can also be limited by quasi-particles. And again, at high temperatures, it sort of follows what you expect from this exponential dependence. And at low temperatures, you find a saturation. So basically, in all experiments, you observe that at sufficiently low temperatures, you have too many quasi-particles, and you don't know really where they come from, how to get rid of them. So I'll show you the main results of our work right in the beginning, and then I'll take you step through step how you get to them. So what we wanted to do is, well, the observation is you always have too many quasi-particles, and those are harmful for basically all sorts of operations you want to do with the superconducting elements. So it's interesting to know where do they come from and how to limit them. So we have a theoretical model which relies on the fact that you always have some non-equilibrium process that will inject quasi-particles in your system. And then the idea is you have to get rid of them somehow to get to equilibrium. So you have a generation, and then to get rid of them, you basically need to recombine two quasi-particles into a Cooper pair to eliminate them. And it's some balance between these two processes, which will tell you how many quasi-particles will remain. So what people usually look at is you think you have delocalized quasi-particles above the superconducting gap edge, and then you can easily find that the residual concentration, because you need two quasi-particles, it's basically a density squared that you need to annihilate. You have an dependence, which is the square root of the injection. So if you screen your system, you inject less quasi-particles, you can bring down the concentration of residual quasi-particles quite efficiently. What we find is as soon as you have this order, you will get also localized quasi-particles, which are fairly close to the gap edge. And those will actually annihilate or recombine much slower. So that means once these quasi-particles is the main thing you have left, your shielding will become much less efficient. The concentration will go much slower the better you shield the system. Surprisingly, what we also find is then if you look at this in a mesoscopic system, meaning in a finite size system, these residual quasi-particles, if spin relaxation in the system is not too fast, will actually tend to polarize. So I want to first explain this model, how you get this residual quasi-particle density, and then talk more in detail about their spin properties. So, well, non-equilibrium quasi-particles can come from all sorts of sources. You have electromagnetic radiation, you have natural radioactivity, cosmic rays. Everything that has enough energy to break Cooper pairs basically can generate additional quasi-particles in the system. So how do you get rid of them? Usually they're not created at very low energies. They may be created at very high energies. But phonons in the system can relax their energy pretty fast, and they will fall down all the way to the gap edge, that meaning all the way until there are no more quasi-particle states available. Once they're at the gap edge, well, there's no further energy relaxation. To really get rid of them, you have to annihilate quasi-particles, again by phonons or electron-phonon interactions, but it means you need two, and they will form a singlet Cooper pair. So the annihilation rate will depend basically on the overlap of the wave functions of your two quasiparticles that you will annihilate. And if you assume that these are delocalized quasiparticles, you basically just get a density squared out of that. And that gives you this dependence that I showed you in the beginning, that the concentration will go as a square root of the injection. Now, if this was the picture for a clean superconductor, if you introduce disorder, just conventional potential disorder, well, the basic knowledge is that you have Anderson's theorem, and which tells you if you have non-magnetic disorder, nothing much should happen. This is definitely not true at large disorder. Here I show you an experiment which actually measured in a very disordered superconducting film the gap amplitude, and you see that in this very disordered limit you have large fluctuations of the value of the gap in the superconductor. Now it turns out this is not specific to very disordered superconductor. Even if you look at slightly disordered superconductor, you always get some mesoscopic fluctuations of the gap edge. But the cleaner the superconductor, the smaller this thing is. So you get some fluctuations which are depicted schematically here. You have your delta of the clean superconductor, but the spatially dependent delta in this disordered system will fluctuate somewhat around this value. When you then look at what are your quasi-particle states, well, you have states that can live below the delta because you have regions where the gap is smaller. These states will overlap and they will form like an impurity event close to the gap edge. So this leads to a rounding of your BICS superconducting density of states and a slight shift in the gap edge to lower energies. So this is on a mean field level. It turns out beyond this mean field result, you get some rare optimal fluctuations where your gap is particularly suppressed. And you can generate localized states in these optimal fluctuation regions, which are below this mean field gap edge. So you'll not get a sharp gap anymore, but some tail of localized states below the mean field gap edge, which is exponentially small, so you don't necessarily see it if disorder is small enough in the density of state. But it means now your density X state, in principle, extends all the way to zero. The states just get rarer and rarer the deeper you go in energy. But you have states available at all energies, and these are localized states. So what does that mean for our recombination process? Well, before I told you the energy relaxation will end at the gap edge. Well, now there are more states available, so they can actually relax into deeper states, and they can relax particularly into these localized states. So then you think, well, the energy relaxation will stop once there's no more states available. And in particular, well, here I show you there's always states available, but they're not necessarily at the same point. So the place where relaxation will stop is when there are no more overlapping states at lower energy. So then you can't relax into these deeper states anymore. So there will be actually some characteristic energy for a given disorder distribution where this relaxation process typically stops, which is when there are no more overlapping states. And at this energy, these are localized states, so they have a localization radius with typically of the order of a few times coherence length. So your fast processes will end at some point, and then again you're in the same situation before. If you really want to get rid of the quasiparticles, you have to recombine. So you have to find another quasiparticle and can recombine with. So now what's different from before is these are not mobile quasiparticles anymore. They're localized, and they will be localized in different positions. So the overlap of their wave functions is not just determined by the quasiparticle length, but it really depends on where they are localized. So what we assume for a simplified model is they're injected somewhere, and then they will stay at that position, basically. They fall in some localized state that's available where they're created. And then they will annihilate pairwise, and now the annihilation rate will depend on the distance, on the distance between the localized states they fall in. So this is this big R. And again, it's the overlap of the wave functions. Now, if you assume that a certain shape of this localized state, you will find, or quite generally, you will find this, since it's exponentially localized, this annihilation rate then will decay exponentially between the distance, as a function of the distance between these localized states on the scale of the localization length of these states. So that means if your density is small enough that the typical distance between quasi-particles is larger than this localization rate is, your annihilation is exponentially suppressed. So you find if the density is sufficiently high, that means the density of quasi-particles is sufficiently small that you don't care about this exponential factor, you get the same result as before. But as soon as the density is sufficiently small, such the typical distance is larger than the localization radius of the particles, you have this exponential suppression of the rate, which then gives you a concentration that depends on a logarithmically on the injection rate. So that means it will decay much, much slower if you reduce the injection rate, and you will get a larger concentration than what you expect from this rate. And well, if you look at this, if you want to model this, you find you have a characteristic length scale, which is now the localization radius times this logarithmic factor that I showed you before, which is basically the space per particle you have for this density. If the density is much larger, if the distance between particles is smaller than this characteristic scale, there will be rapid annihilation, whereas if the distance is larger than this characteristic scale, there will be very slow annihilation. So because of this exponential dependence, you have a clear distinction between particles basically that can annihilate and particles that can't annihilate. So you can make a simple toy model basically where you use this characteristic distance basically as a sharp cutoff. If particles are closer, they will annihilate immediately. If they're further away, they will stay forever. What that means, you can describe each quasi-particle basically as a bubble with a radius r over 2, and two bubbles can't overlap. If they overlap, the centers are closer than r, so there will be annihilation. If they don't overlap, the centers are further away than r, and they can't annihilate. So you basically fill your space with these kinds of bubbles. So the small, the dark ones is the radius r. It means each bubble basically has a shadow region where with the radius r over 2r. If you place an additional particle within this shadow region, the two can annihilate. If you place it outside, the two can't annihilate. And two examples are shown here. So if I place an additional quasi-particle here, the two will annihilate. If I place it at position B, which is outside, the additional quasi-particle will stay. So with this, you can easily estimate what will the density. Basically, you can define a quasi-particle relation by a packing coefficient of these bubbles. And well, if the shaded region is the same as the white region, that means your probability of ending up in either of them would be the same. So that means if you inject additional quasi-particle, you wouldn't change the density. So the naive estimate for this packing coefficient would be just 1/2. You fill half of the space with bubbles, the rest is empty, then your concentration wouldn't change. As you already can see in this picture, actually the bubbles can slightly overlap, the bubbles of radius r. So if you do a numerical simulation, we actually find a packing coefficient that's slightly larger than 1/2. But so this is the prediction in this regime for the concentration of residual quasi-particles. We can do also a full simulation of the model where you really have this exponentially decaying annihilation probability. And what I'm showing here is different curves where I've taken the typical value of the electron phonon coupling for aluminium and different values close to the coherence length for aluminium for this localization radius of the particles. So what's shown here is the residual density as a function of injection. This dashed black line is this quadratic dependence that one would get for delocalized states, and one see the red curves deviate sooner or later for small injection rates from this quadratic dependence and give a higher concentration. Now the question is this really relevant for the experiment, this one in the right regime? The typical value for residual concentration that's usually measured in the system is about 1 or a few particles per micrometer cube, which would be this blue line. To estimate the injection rate is a little harder. If we assume you can screen everything apart from cosmic radiation, we can estimate what is basically the minimal injection rate that you can get, which comes from cosmic radiation is dominated by muon. You know the energy, you know about their flux, and the stopping power in aluminium, which would give a rate, an injection rate shown here, which corresponds to the star here. So you likely would be in the regime where you have already deviations. So if you don't screen well, the localized model would work, but the better you screen, you might end up in a regime where you already have large deviations from this naive estimate of the concentration. So now let's go to the second part. So far, we neglected spin completely. We said if you have two quasi-particles, they can annihilate. Well, actually, when they annihilate, they create a Cooper pair, and the Cooper pair is a singlet Cooper pair. So the spin of the quasi-particle matters as well. So the two quasi-particles can only annihilate if they are in a singlet state. So we try to extend our model now to include spin, and the easiest thing to do is just use a classical spin. Basically, we start from this model with our bubbles, but assume now that each one has a degree of freedom, so it's either up or down. If the two bubbles have the same spin, they're both up or both down, they can't annihilate. If one is up, the other is down, they can. And then do the same we did before. And we found that it doesn't change the dependence on parameters, it just increases the value of this Packington coefficient. Basically, the idea is now bubbles with the same spin can overlap as much as you want, but as you have a random system, you still likely create neighbors which have opposite spin that will annihilate. Again, you have a system, you inject them at random positions. If there's an overlap between the bubbles, they will annihilate. Well, if there's an overlap and they have so the model is you inject particles at random positions with a random spin. Now, then you check whether it overlaps with an already existing particle in the system.
The two spin directions overlap each other. Isn't like two different systems with lower injection rate? I mean, how does the upspin know about the low spin, the downspin?
Well, the model is just, I mean, the annihilation is by electron phonon, and it will couple.
But only for the same spin?
For the opposite spin.
For the opposite spin?
You want to create a singlet, so it's up-down. Okay. So as long as you're in the same system, the particles don't know about each other, so you can pile them up one on top of the other. If they have opposite spins, they will annihilate. So this allows one to increase the packing coefficient just because you can pile up particles of the same spin and they can't annihilate, but you get large fluctuations. And so here is basically as a function of simulation step. Here is more an average as a function of the polarization. So the difference between up and down spins that you have in your system, you can actually increase the density. If your system is more or less polarized, you have more particles that you can pile up, so the density is larger when your system becomes polarized. But it's a fluctuation effect on this classical level. Now this is without spin flip. If you introduce spin flip, then eventually if the spin flip is fast enough, you will get back to the model without spin, because if you flip randomly, basically the spin doesn't matter anymore. So you have a crossover between these two filling fractions, the one for particles with spin and the one without spin, as you increase the spin injection rate.
What would be the mechanism of spin flip? You assume that you have something that...
Assume that there's some spin orbit coupling, and then with you can have inelastic spin relaxation close to the gap edge. The elastic process is actually blocked due to coherence factors, but you can get inelastic processes. Yes. So the idea is that you can probably go to a limit where the spin flip is actually fairly small.
What about RKKY interaction? That's long range. That could also have all of the spins, the localized spins would be interacting with each other in almost any metal.
If it's just between the quasi-particle spins, you basically can't get spin out of the system, so the total spin of the...
Yeah, but if they're all random, if they all arrive with random spin, presumably RKKY interaction could all have them all flipping between them, and then nearby ones could annihilate. I don't know.
Yeah.
That could give a, I mean, I think that would be captured by this sort of rate.
I think for random, that in the end would look like a random spin flip in that sense.
But we get finite rate even if it's even if there's no spin orbit. That's what I'm thinking.
Okay. Yeah. No, we didn't think about that. Yeah, we should probably estimate other processes as well.
Hyperfine coupling be important thing, like the direct Fermi contact potential.
Basically, if the particles are localized, they will have, once they're at their position, they will have some specific spin. It wouldn't fluctuate much. I mean, yeah, there can be other contributions, but I think most of them will likely be small. I mean, yeah, it's not important that, in a way, this is the bare spin. You can have some effective spin once it's at a localized position. This might not change anymore. So if it stays at the same localized position.
So, Julia, localized classical spins generate Shiva states. So, is that
so I mean, in a way, these are already subgap states. So you have if you have a quasi-particle, indeed, you should think about whether the fact that you have additional quasi-particles further modifies the density of states. So it's likely, in a way, that if it's already localized, if you localize a certain spin, it might dig itself in deeper. We didn't take into account that. So we didn't do any self-consistency, taking into account that the gap is modified by the presence of excess quasi-particles. Okay, but we wanted to do better than just the classical spins. So the question is, what happens if we actually consider quantum spins? So we first tried to do this with the same model, actually, with the bubbles, but now we have a quantum spin. And what you can have to define then to consider this is what's called a cluster. What we said is that particles with different spin can't necessarily overlap. So if you have overlapping particles, that means this cluster will be stable only if no pair of particles is in a singlet state. And that's the case if the entire cluster is polarized, so it has a maximal spin. So a cluster is stable if it's in a maximal spin state. Now what happens if you add an additional quasi-particle that overlaps with this cluster? Well, if it has the same spin, nothing happens. You just increased the size of the cluster by 1. If you add a spin which has the opposite direction, you actually have two possibilities. Either it annihilates with one particle from the cluster, or it creates a new cluster with an additional particle, but where the spin direction is slightly tilted. The easiest to see that is actually if you have just two particles. If you add the two particles, you have 3 triplet states. You have only one singlet state. So if you add the particle with opposite spin, you still have the spin projection 0 spin triplet. So here, you just slightly rotate the spin if you add to a large spin one particle with an opposite spin. So that means actually, if you inject particles with a random spin direction, the probability that you increase the size of the cluster is larger than the probability than 1/2, meaning the probability that you decrease the size of the cluster. Because there are more fully polarized states than not fully polarized states, because you have this possibility of tilting the spin axis, it's more likely that your cluster will grow if you add a random spin particle to this cluster. So you have a tendency of clusters to grow if you don't have any spin relaxation. Now, if you have a large system, you will likely have clusters that build with different spin directions, and then a new particle can connect these two clusters, and that will limit the growth of such a cluster, because this other cluster typically doesn't have the same spin, and then you can annihilate in this case. But it means if you have a small enough system that you can get a single cluster, this cluster will actually have a tendency to grow. If it's not limited by any spin flip or anything, it will just keep growing as you add particles, because you always have more states that are stable than states that can decay. Which means that you have a tendency to spontaneously polarize your system. All the spins will point in the same direction. That's when your cluster can't decay, and accumulate them in a small system. And we did some simulation on this bursting bubble model, but actually, once we consider this, the fact that the particles are localized is not that important anymore. Now, the relaxation is not blocked by the fact that they are far away from each other. It's blocked by the fact that they're not in the correct spin state to actually annihilate. So that means we can actually devise a more general model where we just assume that we inject particles in a box. They all interact with each other. So if they're in the spin state that can recombine, they would recombine. But we take into account the spin properties. So we have possible processes. You have incoming quasi-particles. And as we said, it changes now if you add a quasi-particle, it changes the number of quasi-particles. The other number that you have to keep to describe the state of the cluster is the number of flipped spins. So how much does this total spin of the cluster deviate from its maximum spin, n/2. And from what we said before, the probability that you don't create a spin flip is larger than the probability that you create a spin flip, so that you create a cluster that doesn't have maximal spin, which is this process that I showed before. And then you have your singlet annihilation, and then we added two processes that can limit this growth of the cluster. The one are spin flips, so spin relaxation, and the other one, if you have spin-orbit interaction, you can also annihilate triplets by this. So these are two possible processes that will limit that growth. And you can write a balance equation for the number of particles and now the number of flipped spins. If you just look at a stationary solution, combining those two equations, you will find if the spin relaxation is the limiting mechanism, you find a number of particles which is proportional to AV. So it's in a way the same depends on the injection as for the delocalized system, which is the case now. And under certain conditions, the number of flipped spins is much smaller than the number of particles. That means the system is polarized, which means you get a polarized state with a large number of particles under these conditions. You can do the same in the regime where the main limiting mechanism is this triplet annihilation. Again, you can find a parameter regime where the number of particles is large and the polarization is large of the system. So to summarize this, we can draw a phase diagram. We have three now normalized parameters. So we have one characteristic number, which is the maximal spins you can have in the polarized state, which is basically given by the ratio between the usual annihilation and the spin triplet annihilation. The volume in which you can realize that is limited by the spin flips. So you need to be smaller than some critical volume, which is limited by the spin flip. And the injection rate below which you can have this polarized state is limited by the triplet annihilation. So you have three characteristic quantities. You get this phase diagram. These are not transitions. These are very smooth crossovers between a polarized state and an unpolarized state when either the volume is larger than the critical volume or the number of particles is larger than this critical number NC, which is the case, again, when A is larger than AC. In the unpolarized state, you find basically the same result I showed you before for spinless particles. And in the polarized regime, you find these two different dependencies on the injection, depending on whether spin relaxation dominates in this regime or triplet annihilation dominates in this regime. If you compare the expression, you find that this is an enhancement also of the number of particles you have. Again, to see whether this is any realistic, we need estimates for all these parameters. So the estimates are again for aluminium. So I'm assuming that the spin-orbit coupling is again what gives this triplet annihilation. The typical value for this dimensionless spin-orbit coupling is 10 to the minus 2. So I get a maximum number of particles, which can be 10 to 4. The estimate for the volume is about 10 to 2, 10 to 4, the coherence length cube. Here, well, the value of gamma enters, and the spin flip, as I said, it has inelastic. We have in addition some characteristic energy scale, which is like an effective temperature, which is harder to estimate, so there's more uncertainty on this. And then the two combined give the value of the injection, which is actually very huge. So most likely the limiting factor will be spin flip and not a striplet annihilation. Again, as in the classical case, beyond that spin polarized, we have actually very large fluctuations. Fluctuations are of the order of the average number of particles. With that, I come to the conclusion. So what we're predicting is that if you have disordered superconductors, you have an extremely slow annihilation of quasiparticles, which means leads to a large concentration of excess quasiparticles. So the typical strategies to reduce the concentration might not be very efficient in this regime. You can rather think about exciting these quasiparticles out of their traps to faster annihilate them, which might be useful. The question then that we didn't address yet is how does it actually observe physical observables? If they're really deeply localized, they might not play any role at all, but these states are actually very close to the gap edge, so they can easily be kicked out of their traps and then still disturb the systems. Most likely this is not very uniform, so you have large spatial and time fluctuations. The role of spin is quite interesting. You get a non-equilibrium mesoscopic scenario for spontaneous spin polarization, so there's no thermodynamics in here. There's nothing stable about this thing. It's just it's a purely non-equilibrium effect. The consequences is that you, in a small system, you will have more excess quasiparticles even than in the bulk, and it could lead to some spin noise because the spin direction of this cluster is actually diffusing. Thank you for your attention.